Alright, welcome to our first in the series of videos regarding Monte Carlo integration. To start out, let's just look at a simple problem of trying to calculate an area that is somewhat arbitrary. In this case, we're talking about the area here indicated by B, and it's kind of a strange area, squiggly there. And the overall area of the box is the set A union of B. In other words, A is just simply what's outside of B. The question would be, how do we get the area of B if we know the area of A union B, or to say we know the area of the box? Well, here are some strategies. One strategy is we might chop this whole box up into grid lines, as I'm doing here. Equally spaced, even if they don't look equally spaced, they're intended to be so. And what I might ask is what proportion of the boxes overlap the area B, and I could count them, right? So I could count all of the boxes that overlap B, and I could look at the number of squares that overlap B, and divide it by the total number of squares that were created by my grid. In doing so, I come up with a proportion, the proportion of grid squares that are touching or overlapping B. Or I could also take, if I wanted to, the number of squares that are actually inside of B. The difference here would minimize, become trivial as the number of squares goes to infinity. We get a really, really dense grid. But the idea is getting some way of calculating a proportion of something about B relative to A. In this case, we're taking the number of squares that overlap. I could take the number of squares that are inside. I could also look at the individual crossing points, such as that little cross point there. Look at all the points at which the grids cross each other. Those are just individual points. And count the number of points that are inside B relative to the total number of points, which would be this one. Go back here to my different pen. It would be this one here. Well, okay, so now I have a proportion, say a proportion of squares that overlap B relative to the total number of squares, or the proportion of points in the grid that are in B relative to the total number of points. And the area of B is then that proportion times the overall area of A union B, or the overall area that I know up here, this whole square. So we take the area of the whole square and we multiply it by the proportion generated above by either this method, or we could use this method. The second one probably the least accurate for a finite number of squares. But nonetheless, we could do either one. And this would give us a approximation or an estimate of the area B. Approximation gets better as this grid gets finer. You can see in the sense of overlapping, as the grid gets finer, here we've got larger boxes, as it gets finer, we would be able to chop up and get a much finer resolution as to the number of boxes relative to the overall number of boxes that overlap the area B. And again, if we use our intersection, same thing. We would take the proportion generated by that equation, multiply it by the overall area, and that's going to give us an estimate here of the area of B. But we could also do something else. Instead of this grids, we could also erase some of this stuff. We could also randomly throw darts at this board. Let's assume this was a wall, or some whiteboard on a wall, or a corkboard on the wall, and this was a splotch of painted B, and I don't know how much area B captured, then I could randomly throw darts at this wall. Now, if the distribution, or the probability of landing in any point here, is the same, so it's kind of a uniform distribution across the full area of the square, and I get a point here, and then I get a point there, and another point, and I keep randomly throwing, and I get points as I randomly throw. Well, I could then look at the number of dots that landed inside of B relative to the total number of dots that I had generated, or the number of darts if I'm actually throwing at the wall. And that gives me another way of getting a proportion. So from that perspective, we could also use random points and generate my P, which I can then use relative to the total area to get another estimate of the area in B. Well, this one here with the random points is essentially the basic idea of Monte Carlo integration. Throwing darts. That's pretty much what we're going to do, although we're going to let the computer throw the darts. So let's think of it this way. Let's suppose that I have a function indicated here, a function of x. And this function, we'll just call it just g of x, what arbitrary function it is. And I want to be able to integrate the area under that function from 0 to x naught. And let's suppose that I know that I can find a yc that, as a constant, dominates the whole area. All right. That means that if I take yc and I multiply it by x naught, I get a known area for that square. Right. So I can get a full known area for this square here. And what I want is to know the area of g of x within this range from 0 to x naught. Well, I could randomly generate points in this space, which means randomly generate xy points, and I can look at the number of points below g of x, I'm calculating this right here, relative to the total number of points that I generated. All right, so I randomly generate xy points, and I get various points here, randomly generated, and I look and I say, well, what proportion of the points fall below my curve, which would be the area under that curve relative to the overall area. So my integral is estimated approximately here as that proportion times the area. Notice this is in fact my area, although I guess I could say yc, so I suppose I should call that, instead of c times x naught, it's yc times x naught. And this p is the p right here. And that gives me an estimate. So for example, in Stata code, I could generate a y, which is my constant c times a uniform, and that's going to generate randomly points that go between, since uniform is on 0 to 1, it would be randomly generated points all the way from yc to 0, right? If I take the constant yc, here I'm calling it c, but let's say that constant, and generate let's say I had set the observations for Stata to equal to 1,000, and I would generate 1,000 points between 0 and c. Here I would be generating 1,000 points between 0 and x naught. I could then generate an indicator as to whether or not y is less than or equal to g of x. So for each point of x, this is assuming that I can actually calculate g of x, so we're making that assumption here at this point. And my indicator here would be whether or not y is less than. If I then sum pi in Stata, and then assign a scalar the value of the mean of that sum, which is essentially the proportion. This is an indicator. Indicator means that it's equal to, so IP is equal to 1 if y is less than g of x, and 0 otherwise. And consequently, the mean of this dichotomous variable is going to be the proportion of points that have y less than g of x. I can display or just show in Stata, if I want to know what the area is, I can then tell it to multiply my calculated proportion times the constant c times the constant x naught, remembering that this is that total area, the total area. And the p times that will give me the area under the curve. Another thing to notice, which we will move into right now, is that I'm trying to integrate from some points a to b. In this case, it was from 0 to x naught. Some function g of x dx. And I might be able to express x as a function of a uniform variable, which is to say, if we let u essentially be a variable that is on the unit interval. And the function is 1 to 1, let's presume, so we can write it as a function of u, and we can invert that, and we can say that u is therefore some function of x. We notice that dx du is the derivative of h with respect to u, which would mean that dx is that derivative with respect to u times du. So I can plug and chug. We take the information I have here, I plug it into here, and reconvert it, transform it to this integral. So on the variable of u, my u value in the integram is u evaluated at a, right, which we've got here. That's my u. And u evaluated at b. My g of x up here is going to be g evaluated at x, which is a function of u, so now it's a function of u. And my d of x, come all the way around, is dx du times du. Which means that now I have, you can think of it as a new function. This whole part here is some new function, say, whatever, some new function of u du with an integral at the various integrand values. So I've converted a integral in terms of x to an integral in terms of u, which is on the unit interval. So this will be the basis for our next video in this lecture, and it will be looking at how we can use this transformation to be able to easily calculate certain kinds of areas and certain kinds of integrals. So you will need to go on then to the next video for the next segment of this video.